Breaking, Curiosity rover, unearths evidence of ancient carbon cycle on Mars, a game-changer for habitability studies. Could the secrets of Mars' past hold the key to Earth's future? Join us as we delve into the groundbreaking discovery that's rewriting the story of the Red Planet. In a landmark study published in the prestigious journal Science, researchers have unveiled compelling evidence of a past carbon cycle on Mars, a discovery made possible by NASA's intrepid Curiosity rover. This monumental finding sheds light on why Mars was once habitable, and crucially, why it eventually transformed into the desolate world we observe today. The key lies in the sequestration of carbon dioxide, CO2, within Martian rocks, leading to a planetary freeze. The implications of this discovery are profound, offering invaluable insights into planetary evolution and the delicate balance required for sustained habitability. For space agencies, researchers, science enthusiasts, and students alike, this is a pivotal moment in our understanding of Mars and its potential for past life. As Curiosity diligently traversed the slopes of Mount Sharp within Gale Crater, it stumbled upon significant deposits of carbon locked within carbonate minerals. Specifically, the rover identified siderite, an iron carbonate, present in concentrations ranging from 4.8 to 10.5 weight% in drilled samples. This discovery, made in late 2022, occurred within sedimentary strata rich in magnesium sulfates, a region previously mapped from orbital observations. To analyze these rocks, Curiosity employed its sophisticated chemistry and mineralogy Chi-Min instrument. This instrument utilizes X-ray diffraction to precisely determine the mineral composition of the samples, providing crucial data for understanding the geological history of the area. The presence of siderite in such quantities is a game-changer, offering a tangible explanation for the missing carbon on Mars. For decades, planetary scientists have grappled with a fundamental question: where did all the carbon go on Mars? Evidence strongly suggests that early Mars possessed abundant liquid water and a warm, inviting climate, sustained by a dense atmosphere rich in carbon dioxide. However, present-day Mars is a stark contrast, a frigid, arid desert with a vanishingly thin atmosphere. The prevailing hypothesis pointed towards the sequestration of carbon dioxide in carbonate minerals. These minerals, composed of carbon and oxygen, were considered the most likely repository for the missing carbon. Yet, despite extensive observations and analyses, scientists had failed to find sufficient carbonate deposits to account for the planet's dramatic transformation. Dr. Ben Tutolo, the lead author of the groundbreaking study and an associate professor at the University of Calgary, emphasizes the significance of this discovery. "We found it here, for the first time. That really is the crux of what's exciting here." This finding finally provides a concrete answer to a long-standing puzzle, revolutionizing our understanding of Mars' climate history. The analysis of the Martian rocks revealed not only the presence of siderite, but also varying amounts of iron oxyhydroxides. These compounds form when siderite undergoes dissolution in acidic water, indicating that some carbon was indeed released back into the atmosphere, creating a rudimentary carbon cycle. However, unlike Earth's carbon cycle, which has maintained relative stability for billions of years, the Martian carbon cycle was characterized by a significant imbalance. The surface rocks absorbed far more carbon than they released, leading to a net depletion of atmospheric CO2. Dr. Tutolo succinctly explains the consequences of this imbalance. CO2 goes down, it doesn't come back up. This helps us understand why Mars was once habitable and why it became uninhabitable. The Martian carbon cycle, therefore, serves as a cautionary tale of how a planet's climate can be drastically altered by imbalances in its geochemical processes. The discovery of substantial siderite deposits has profound implications for our understanding of Mars's ancient climate. Climate models suggest that early Mars required at least tens of millibars of atmospheric CO2 to maintain a temperature conducive to stable liquid water on its surface. In stark contrast, the current Martian atmosphere contains a mere 6 millibars of CO2. If the amount of siderite identified by Curiosity is representative of similar deposits distributed globally within other Martian sulfate-rich strata, scientists estimate that these deposits could have sequestered the equivalent of 2.6 to 36 millibars of atmospheric CO2. This level of sequestration would have been sufficient to trigger a dramatic shift in Mars's climate, leading to the planet's eventual cooling and loss of habitability. As CO2 was progressively locked away in rocks as carbonates, the planet's temperature plummeted, rendering it inhospitable to liquid water and, potentially, life. This scenario underscores the critical role of atmospheric CO2 in maintaining planetary warmth and the potential consequences of its depletion. Intriguingly, this Martian discovery has direct relevance to ongoing efforts to combat climate change on Earth. Dr. Tutolo's research focuses on developing methods to transform human-generated carbon dioxide into stable carbonate minerals, effectively locking carbon away in rock formations. What we're trying to do on Earth to fight climate change is something that nature may have already done on Mars, Dr. Tutolo explains. Learning about the mechanisms of making these minerals on Mars helps us to better understand how we can do it here. Studying the collapse of Mars's warm and wet early days also tells us that habitability is a very fragile thing. The Martian carbon cycle, therefore, serves as a natural experiment, providing valuable insights into the processes of carbon sequestration and their impact on planetary climate. By studying the successes and failures of Mars's carbon cycle, we can gain a deeper understanding of how to manage our own planet's climate more effectively. NASA plans to continue exploring sulfate-rich regions on Mars through future missions and further analysis of existing data. These efforts aim to confirm the current findings and refine our understanding of the planet's early history and its subsequent transformation following the loss of its atmosphere. The ultimate goal of this research is to determine whether Mars was ever capable of supporting life. The discovery of the ancient carbon cycle brings us closer to answering this fundamental question. Dr. Tutolo emphasizes the significance of this discovery in the context of Martian habitability. It tells us that the planet was habitable and that the models for habitability are correct. The broader implications are the planet was habitable up until this time, but then, as the CO2 that had been warming the planet started to precipitate as siderite, it likely impacted Mars's ability to stay warm. The discovery of substantial carbon deposits within Gale Crater represents a significant leap forward in our understanding of the geological and atmospheric evolution of Mars. It provides compelling evidence that Mars once possessed the necessary conditions for life, including liquid water and a warm climate, before its carbon cycle became irrevocably imbalanced. As we confront the challenges of climate change on our own planet, Mars serves as a stark reminder of the fragility of planetary habitability and the potential for its loss. The remarkable aspect of Earth is its sustained habitability for at least 4 billion years. Something occurred on Mars that did not occur on Earth, and comprehending this divergence is crucial for safeguarding the future of our own planet. Are you inspired by the groundbreaking discoveries on Mars? Here's how you can get involved. Share this exciting news with your friends, family, and colleagues. Encourage them to learn more about Mars and the importance of planetary science. Together, we can unlock the remaining mysteries of Mars and gain invaluable insights into the future of our own planet.